All right, so we're going to imagine a new way of slicing up stuff. It's called shells. And I have a very simple question for us first. What is the volume of this piece of paper? Like the actual paper, like the dead trees. How much total volume is in this piece of paper? And that'll come in handy in just a sec. Well, ignoring the holes, can you say this is basically a very thin box? So it's a box, and its volume is length times width times height. And depending on how you want to count it, maybe the height is very, very small, right? Like 1/10 of a millimeter or something. Probably less. I haven't measured a sheet of paper in a long time. So if I want to think about it like this, the height is very small. If I want to think about it like this, I guess you'd call it the length, or the width is very small. So now here's my next question. What if I take the sheet of paper, which is currently a box, volume, length times width times height, and I curl it into a cylindrical tube? Now what is the volume of the paper? Not the inside of the cylinder, not where you would hide a soda can or something, but what's the volume of the paper itself? Would you agree it's still the same volume, just kind of curved? So we'll say curl it into a cylindrical tube. Which is also called a cylindrical shell. Nothing to do with clam shells on the beach or whatever. And it still has the same volume, right? Let's draw what's going on. So we had a shell like this, cylinder like this, and it didn't have an infinite thinness to the boundary. It had very slight thickness like that, right? All the way around like this, all the way around like that. So we could talk about its radius and its height, and how does this map to the piece of paper? What was the long edge of the paper here became the circumference. And what was this edge of the paper became the height. So we'll say the for this piece of paper it was 11 inches. The height now is the 8.5 inches. And what about this very thin part? Up there I called it the height, but now we could call it the width is maybe 0.1 millimeters. So that's one cylindrical shell. And then the question is, what am I going to do about approximating this thing? I'm going to imagine slicing it up into a bunch of concentric cylindrical shells, each with its own height. So what I mean is not just the aluminum form here, but if it had been actually a cake, instead of slicing the cake the regular way like wedges, or slicing it horizontally, almost like you would slice a bagel, we're imagining slicing it concentrically. So I have the world's best visual aid here, a stack of Dixie cups. There's 5 of them, and I've colored the edges red, orange, green, and then inside is blue and purple. So we've got a very thin Dixie cup, a very short Dixie cup kind of on the outside, and then the next one inside is a little taller, and then the next one inside that is the tallest, kind of like the vertex of that bundt pan, and then the next one inside that is a little shorter, and then the next one inside that is even shorter, kind of like the bundt pan. So these are Dixie cups. Their edges are a little slanted, but pretend that they were straight up and down like cylinders. So that we've got all those concentric cylinders. So now let's draw our bundt pan sliced up that way. So now we're saying take a slice here, which is like an edge-on view of the piece of paper, and rotate it around like that. Now we're rotating around the y-axis. So what's the volume of this shell? Not this part inside the shell, but like the paper itself or the Dixie cup surface. Well, the volume of the piece of paper was length times width times height, or length times height times width or something. So we're going to say it's L times H times W. And let's say this is H. And what was L? L initially was the long edge of the paper, which we then curled around, became the circumference. So it's the circumference times the height times the width, which was very, very skinny. What's a good calculus word for very, very skinny? dx. And what's the height here at some particular x value? That would be f of x. And what's the circumference? And going from here out to here, that's x, which is basically the radius of the shell. And what's the radius of a circle that goes all the way around? It's 2 pi r, or 2 pi x. So that's the volume of this shell. And then what's the overall volume of the shape? Well, we would add up all the different shells, starting from a small radius and going to the largest radius we have. So it would be integral from x equals 2 to x equals 12.5. That was out here. Here was x equals 2 of 2 pi x times f of x times dx. So that's the volume by shells formula for this particular case, where we're rotating around the y-axis, but we're given f of x instead of f of y. So the things to notice: we're doing the integral with respect to x, even though we're rotating around the y-axis, which is what we did not do with discs or washers. So we're doing the integral x equals blah 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 dx, even though we're rotating around the y-axis. Another thing to notice, we're not squaring anything. X here is the radius, but we're not squaring it. We're using it to find the circumference rather than the area. So not the radius, which is x, or f of x, which is the height. And then the third thing, before our integrand had, in discs and washers, it was like pi times the radius squared times dx. But now we have a x in there as well. That might make some integrals harder to do, might make some integrals easier to do. We can move, if we need to, we can move the 2 out in front of the integral. It's a constant multiplier. We can move the pi out in front of the integral if that makes life easier. That's a constant multiplier. Can we move the x out in front of the integral? It's a multiplier, but it's not constant. It changes as x changes in this region, so we can't move the x out front.